Okay, cool. It's coming up. Okay. Hello, everyone. This is Jiming Sun. I'm the host for this AI for Health webinar, and also a computer science professor at the University of Illinois, Urbana-Champaign. So it's my great pleasure today to introduce our speaker, Sanmi Koyejo, an assistant professor from Stanford Computer Science Department. And Sanmi is also a co-founder for Virtual AI. At Stanford, Professor Koyejo leads Stanford Trustworthy Artificial Intelligence Lab, or STARE, which works to develop the principle and practice of trustworthy AI, focusing on application to science and healthcare. And Sanmi has been recipient of many awards. I'll just name just a few, including the Skip Alice Early Career Award, Presidential Early Career Award for Science and Engineer, PKs, Sloan Fellowship, and Terman Faculty Fellowship, NSF Career Award, Kavli Fellowship, and HKI Early Career Award Spotlight. And Professor Koyejo has served at the main machine learning board, including NeurIPS Foundation Board, and also Association of Health, Learning, and Inference Board, and also the presidents of the Black in AI Board. Okay, without further ado, and let's welcome Professor Sanmi Koyejo.
Yeah, thanks, Jimeng. And I guess Jimeng didn't mention, but I used to be at Illinois as well, till fairly recently, actually. So we're briefly colleagues for some time.
Yeah, we also have a joint project. So
yes, we have some joint work together. So really excited to be talking to you today about some of the work we've been doing, trying to understand better how to build foundation models that are useful for electronic healthcare records kinds of settings. And so what I'll talk today about, I'll frame out the problem and maybe I'll talk through some of the details, but I do think it's a sort of fascinating direction, and one that does seem uniquely interesting for folks thinking about AI technology in healthcare, in my view, understudied. And so I'll say some of what we think are some of the open questions down this road, and maybe interesting for some of you who are thinking about research projects and open questions. So to get things started, many of you are familiar with electronic healthcare records. Specifically, there's a lot of interest now in thinking about how to build these as foundation models for various kinds of clinical application tests. So broadly at a high level, the idea is that you take clinical text of various kinds, and from this, you construct some kind of clinical language model that can be targeted perhaps either as some generative task. I think more and more are thinking about open-ended question answering of various kinds based on the text, and potentially also the structured data. So structured data and structured text, various kinds of text representations. Or you could also think about using this for various kinds of downstream predictive tests. So I'm mostly focused on the predictive applications of this in this conversation, but as we very well know, there are interesting questions both on the generative and predictive side. I think many of them highly overlapping. And so an example of a generative task, for instance, could be, take clinical notes, synthesize discharge summary. This would be useful for maybe reducing clinician time for administrative overhead that may not be something that requires a lot of human attention, or maybe something that human can check quickly, even if not designed, even if actually written by an AI model. There are also a variety of prediction tasks. So for instance, taking a representation based on a model, asking to predict the risk of a patient developing something like celiac disease using information from clinical notes based on your visit history. So again, many of you are familiar with this as part of the promise of language models, AI models broadly within the clinical domain. And so behind the scenes, again, hopefully just summarizing some of what you might know, what needs to happen is to go from what is actually quite a rich and complex signature of clinical events to something that the foundation model, AI model, machine learning model can process. And so the record itself looks like a combination of things like diagnoses at various timestamps, medications over time, labs that might be drawn to help inform clinical care and diagnoses, procedures that might be done, all the different visits that the patient might have had. Generally, these are, have to be synthesized because they're all different kinds of data. So something like a diagnosis might be represented using something like an ICD-10 code, which is sort of formalized way of capturing different kinds of disease diagnoses, primarily for, or often for reporting purposes, say for insurance. There are medications that go through RX norm, often for an ontology, useful for capturing things like drug dependencies and adverse events and things like that, but often how things are represented. Blank for things like labs, is when you collect labs tied to, again, various visits and parts of clinical care. CBT for lab procedures. What I'm hopefully representing here is sort of really the high diversity of the kinds of information that needs to be ingested in an EHR if you're going to build a foundation model based on an EHR. And I'm bringing this up because I think this is meaningfully different than natural text. And I think this is one of the gaps in the space when we think about the opportunity to build technology that meaningfully answers the questions that we're looking to answer. Because, a lot of our tools use text out of the box, text models out of the box, which are really built for, conversational or often web data, which are mostly, again, very different forms. So single format. If there's a mix of formats, maybe a bit of interleaved audio or video, but, the vast majority of language models really are single mode and mostly informational, say web pages is what they're built on and what they tend to be best at being able to sort of either represent or generate signals from. And we're taking these tools and applying them sort of black box often to EHR data that hopefully, if you're not already familiar, I imagine many of you are, but if you're not familiar, is meaningfully, I'd argue, quite complicated. Just looking at the data representation because of how many data types that you have to represent. And so what happens from this is that you do the standard thing that you do in building learning models, particularly language and foundation models. You tokenize. So you take the EHR data of all the different types, you serialize it in some way. So it has to look like a sequence, at least if you're going to use the off-the-shelf tool. Tokenization is some way to convert the data into symbols that the machine can understand. And then you apply this to existing machine learning and AI, say transformer models, any other kind of sort of learning model that you'd like to build. And the foundation part of this comes from the scale and the diversity of information. But I really do want to highlight the different nature of the signals that you're getting compared to what we typically see for natural data. And so once you have this, then you can feed it through sort of a standard sequence model, something like a GPT, and then you hope to be able to predict or answer questions. So either be able to generate signals for, say, open-ended question answering, or build representations that can help you, say, fine-tune a predictive model. For, in this case, we're doing various kinds of, say, diagnosis, prognosis kinds of tasks that you might be interested in. Okay, so today I'm going to talk through two problems with this broad framing that we've noticed by trying to engage and trying to build AI tools in this setting. And the argument I'm going to make is that these problems point at gaps in sort of the off-the-shelf AI tool sets where I think there are sort of enough meaningful differences that mostly I'll talk through maybe simple approaches to try to mitigate them. But I do want to motivate that I think this is actually quite a rich potential opportunity or direction to think about approaches that might be very specialized to some of the issues that we find when dealing with EHR data. I'll focus mostly on issues that tie to the fact of the longitudinal nature of the EHR data. So first, I'll talk about issues with temporal biases, particularly various kinds of uneven distribution of events that are measured in existing large clinical event data sets that become the back end of, at least open data sets that become the back end of many of our foundation models in healthcare. And I'll talk about one of our recent proposals called Timer, which is both a benchmark framework and then new ways of doing instruction tuning to better capture temporal biases in the data. And then second, I'll talk a bit about other kinds of, again, data-dependent biases. So things that are standard in EHR data clinical note curation, things like copy forwarding, part of the irregularity of time intervals, progressive difficulty, and disease complexity. And my goal here will be try to highlight how different I think these are from most of what you see in standard text, and some early work trying to use longer context models as a mitigation for some of these issues. But again, I think about this more as an exposition, something that I think is somewhat obvious, but highlighting that these seem to matter a meaningful amount in the results that we're getting out of these models. And I think an opportunity for new work beyond ours for moving the field forward. Okay, so first I'll talk through the timer work. So this is work with some excellent colleagues led by Heije and Alyssa, who Heije is a postdoc here with Nigam Shah. Alyssa is co-advised by Nigam and I, and awesome colleagues, some of whom you might know, were for this recent work that we just finished. So the motivation here is thinking about some of our observations of EHR data and how this ties into trying to do useful things and building foundation models, doing things like instruction tuning for improving performance for generative open-ended tests. So first, most EHR data is single visits and fairly short in temporal coverage. So if you look at things like mimic records, which are, again, by far the most sort of common database that people use to build foundation models on top, because, again, these are the public data sets. So these cover ICU patient visits, but they tend to be per individual, fairly short duration. So on average, you're looking at 7.2-day duration, which is much, much less than what you'd expect to see. I mean, part of this is the fact that it's an ICU, so it's meant to be sort of these kind of rapid interaction. But also more broadly, I think very different than what you'd expect to see if you're trying to build a tool that engages meaningfully in what clinical care looks like, which generally has a much longer duration. In addition, they tend to be single visits. So some of the order of 80, almost 85% are single visit patients. So you're not seeing this recurrent signal that you'd expect to see in sort of, to capture ecological validity. So capture real world interaction signals that you expect to see from individuals engaging in the healthcare system. So an example of this, again, shows up in Mimic. Another limitation is in many of these benchmarks, there's a ton of recency bias. So the distribution of visits that happens in the data set is if you look at the distribution over time. So the visits have, they're somewhat biased towards maybe recent visits, but the bias is not terribly strong. But if you look at the instructions and like the way that we build benchmarks to check how well you can, say, get a model to follow instructions to answer some questions in clinical settings, most of those distributions are actually extremely biased, recently biased. So if you look at existing benchmarks and databases, some like 71% are focused on retrieval kinds of questions, which are these kinds of, can you answer some signal that's hidden in a long or in some clinical note? They are very tied to, can you answer this for generally sort of recent visits? So they have this recency bias in it, which leads to this high skew where something like, over 10% is, order the last few positions. I'm illustrating here this blue part of the, I'm not sure actually if my cursor shows up. But again, this sort of strong recency bias in existing instruction tuning data sets. And also this addition of how we think about measuring context effects. So think of this idea of needle in a haystack. So asking questions for information that's hidden in long instruction. And so we think these create meaningful challenges. The short time frame, the single visits focus, the recent context bias actually leads us, one, to have bad measurement of where the tools can be useful. Because I say this because often the real tasks that we want to use these for don't have these properties, yet often our data sets and our benchmarks have these properties. So there's this gap that we need to get around. And then even if you sort of take this out of the box and throw it into many modern language models, they end up replicating very much the same kind of issue. So if I, for instance, try to synthesize or engage with models to synthesize instructions or answer questions based on instructions, what we found in case studies, more details in the paper, are issues with understanding temporal boundaries, so what happened where, and making sure that sort of answers correctly reflect and attend to those boundaries. Inaccurate and incomplete trend analysis when information or things are happening over different visits over time. Chronological confusion, so mixing what happened in order. So late things before early things, or early things for late things. Instruction response. All these we think are, again, difficulties we think are partially caused by the model themselves, partially caused by the data sources that we're training on. And so part of our goal here is to explain these gaps, but also think about tooling that can help close it. And so there's a bunch of additional error analysis in the paper. I'll ask you to consider looking in detail if you're interested in additional work. So to this end, we propose two key components. The first is evaluation benchmark that is designed to better engage with, again, what we think is closer to real world clinical use cases. So flattening, if you like, I think most salient for me, this high dependence on recency, the recency bias in existing data sets. So the benchmark takes longitudinal existing data. I think the key thing as a way to accelerate development here is that we use data synthesis. So we synthesize data, but data that where we synthesize in such a way that it's much more temporally balanced. And then we have clinicians verify that the synthesis instructions and response pairs are reasonable and accurate. And then on the back end, to make this a scalable benchmark, we have a variety of different metric types, which include LLM judges, a variety of automated metrics, head-to-head comparisons. So I'll briefly mention some of our sort of results on the benchmark there. And then second bit of this is an instruction tuning model. So this is using some of what we've learned from our analysis of the existing landscape and the gaps in the data set to build new models that are instruction tuned so that they have better behavior to deal with some of the issues that we've already talked about. So we look at instruction tuning tied to various kinds of temporal distributions. So the recency biased instruction, which is the state of the art or the sort of most common practice. But also we look at things like edge focus, we look at uniform distribution instruction and see what those results look like in the model. So I'll briefly talk about these high level, again, with details in the paper, and I'm happy to talk through some of these offline as well. So on the benchmark side, some of the key design principles, thinking about evaluation for longitudinal reasoning. One of them is thinking about multiple time point reasoning evaluation. So here we ask questions that require the model to go through not just a single time point and retrieval, this needle in the haystack thing, but actually synthesize information over multiple visits. So for instance, targeted at, say, cancer treatment, we're looking through initial diagnoses, genetic testing, like again, historical context, all the way tied to, say, the treatment timeline. And so this allows us to, I think, ask more meaningful and I think ecologically valid questions that capture, again, the fact that clinical use cases that we find most exciting should have this sort of ability to reason over meaningful, longer context. In particular, evaluations that focus just on, say, beginning or ends of the records, a lot of signal that we found showing that they can miss important, crucial intermediate events. So again, the idea of building in the ability or requirement to reason over multiple time points avoids this bias of, again, being good at single point retrieval, being bad at synthesizing information across timelines. And so based on this information, we synthesize, so behind the scenes, we use existing data to sort of train or prompt and tune a generative model that takes, we can give it time evidence and synthesize instruction response pairs and make sure that there's this connection between the query, the response, and the ability to query over different timelines at different levels of resolution. And then after this, or tied to this, we do clinician evaluation. So we did this with 3 clinicians. For scaling, we picked 100 random instruction response pairs, and the clinicians were asked first whether the synthesized data had clinical relevance. So there, the most clinicians for most of the questions thought that there was high clinical relevance. Second was a complexity. So how complex, again, tied to this comment I made earlier about the bias of existing models to mostly be good at like question answering and single facts and not being able to capture, again, more complicated temporal reasoning, synthesized facts that require reasoning over multiple visits. So we asked clinicians the extent to which they thought the models captured reasonable temporal complexity. And again, mostly positive results, though not as strong as purely on the relevance side. So this is something we're working to results factually accurate based on the synthesis. And again, we saw the vast majority, so, at least for the random subsample that we evaluated, clinicians agreed for most of the questions that they were factually accurate in the question and the response. And so this comes together in this benchmark that we've now set up and, encourage you to take a look at and potentially engage and use. In addition to clinical verification, it also includes, again, the ability to automatically judge. So this is the scalable part that you can deploy, which includes, again, LLM judges that do some of this same kind of work that we had clinicians do, but also automated metrics and head-to-head comparisons. And so compared to existing benchmarks, this allows for, or this is built so that we can capture multi-visits as opposed to some like Mimic Instruct, which is mostly single visits, much longer time span. So order thousands of days compared to some existing work that's much shorter, as mentioned briefly. It engages with both structured data and clinical notes. The data, as already mentioned, is model synthetic, so maybe different from some like a Metaline, which is mostly human curated. And again, among the largest of this kind of data, but something that, again, we're looking to improve on and scale up even more. And so some of the attributes that we think are important here are capturing instruction, response, and then specifically being able to synthesize in time evidence, so it captures temporal dependence in the signals. Okay, so in order to use this is again targeted at sort of instruction tuning for language models. So the idea of instruction tuning, we use this term a bunch, but under the assumption that you're at least vaguely familiar with it, but I can briefly explain. So the idea here is it's a way to adapt pre-trained LLMs to better follow domain-specific instructions via specialized training on instruction tuning data set. So you can think about this as sort of part of the post-training setup in most language model deployments. This is after you have an initial model, you want to get it better at the task that you're targeting. And so you give it examples of this task and you sort of fine tune the model so it gets better at those tasks. So instruction tuning ends up being an important part of, again, getting models to be good at things. Most of the sort of real world applications of, or what we found, language models in particular, but most kinds of generative models useful, require this instruction tuning to get them from raw generative models to models that are sort of useful for various kinds of applied tests. And so, as mentioned, most of it is focused on short form. Again, the idea of the proposal for this work is to expand on this. And so the modeling part or the model part is to get it better at closing some of the gap that we think don't meaningfully reflect real world clinician needs and real world use cases. So to do this in terms of some of the modeling, so we built a model that can do better instruction tuning. Some of the gap that we needed to cross on the modeling side is to handle the fact that time spans vary a ton, as mentioned briefly. So in particular, on the benchmark side, as mentioned, we went from something on the order of 7 days to something on the order of average timeline being thousands of days and high variance across those days. And so within the model, the way that we capture this is that we have normalized position metric that captures relative temporal position. So this allows for some normalization for the fact that different individuals will have, again, different timelines, but can be compared on the same scale. So it's, again, relative difference in timeline across individuals. And as mentioned, some of what we can now tackle with this tool helps mitigate some of what I've already mentioned of significant distributional bias in existing work on LM instruction, both data sets and models, which again, this sort of bias towards recency, sometimes called this lost in the middle phenomenon, where there's just very little signal, both on the instruction side or on the sort of ability of models to correctly answer questions for signals that are in the middle of the timeline. So early tend to be good, late tend to be good, middle, lots of gaps. So the instruction tuned data set is, a model. So now this is a model that we developed in coordination with, again, this new benchmark that we developed. And so this allows for lots more flexibility. So we can get the model to work in a variety of different temporal settings. So we tested both something that looks a lot like existing data sets, which is recency focused. Here, there's a concentration of the last quarter. This mirrors existing human annotated patterns that we've seen and many of these in data sets. We also looked at edge focus to capture what might happen if there's much more signal close to the LM boundary. So this matches what we saw when we had LMs generate various kinds of patterns. And then we also looked at uniform. So this is explicitly designed to have balance over the timeline for individual going through medical care. And so consistent density, so flatter distribution, if you like, throughout. And so I'm showing some experiments just to set things up. We looked at star OMAP, which is based on an initial data set recently developed and preprocessed with timelines to fit into context windows. So this is a meaningful limitation. I'll talk a bit more about this in the second half of my presentation today, but this issue of context windows and how we can deal with them. Because again, the richer the kinds of signals we're trying to capture, the more we're hitting the limitation of how much context you can fit into a language model. And then finally, we, on the pre-processing side, we filter the benchmark questions to capture the fact that we want this to have multiple timestamps, pieces of evidence. So we have, again, the sort of more complex temporal reasoning. On the model side, we evaluated a variety of existing models, open and closed variants, and then we also fine-tuned our own models. So the second part of the contribution is, again, explicitly instruction-tuned data sets, so they're better at medical tasks across these various kinds of distributions. And then for evaluation, so we, again, used the fact that we have, again, built this benchmark to verify automatically. We have both LLM judge, so this looks at sort of correctness and completeness prompted from the model based on existing evidence. And this is checked, as mentioned briefly, against clinicians' judgment of how well the judge might be doing. We also have some of the standard NLP kinds of metrics, so things like BERT and some of the other Blue Score, Rouge Score, and then we do head-to-head comparisons, models compared to each other. So I'm showing here very quickly, again, many more details in the paper, some of the results. So looking both at an existing, say, meta-line data set. So this meta-line data set, again, has some of the issues we talked about, but we wanted a comprehensive evaluation across both existing benchmarks and new benchmarks. And looking at how well things do as pre and post instruction tuning. So what is the effect of the instruction tuning as described to better align with the use cases, the temporal complexity that I've already outlined. How well it compares to a bunch of existing data sets, and then comparison also both on the existing meta line, but also on the new Timer bench data set, which is again designed to be more complicated so that it again captures what we think of as more clinical ecological validity. So the high level takeaway is that we see meaningful improvements in performance on instruction tuning when we couple in temporal complexity in the way that we built the models. Of course, I think there's still gaps here. So the models do better, we think we're on a sort of meaningful positive trajectory. There's clearly a lot more to do to get these results to be much, much higher. And part of it is the measurement process. We think also we need to build on the measurement side. But on the performance side, I think there's also quite a bit of work additionally to do. I'll say a little bit of some of where we think context could matter. Context size and ability to handle long context can matter in improving these results further. So to summarize the first part of the talk, the key takeaway conceptually for me is that there is meaningful temporal bias in the existing data sets and existing models. And this has a meaningful effect on how well we can build foundational language models for, in this case, generative tasks. And this is illustrated by, for instance, the timer benchmark and some of the pre-evaluation led to the benchmark and the results from the timer instruction models. More broadly, I think meaningful unique properties of EHR data sets, which can affect the usefulness of language models, foundation models in practice. So again, some of the issues I talked about, recency bias, single visit versus sort of longer, multiple visits, temporal coverage. A lot of what we have shown, again, details in the paper, that broadly models seem to anchor on this data bias and so do worse when pushed beyond these directions. Again, we think this is important because this is capturing closer to what we want to use these in the real world for. And so there's a gap there on the data side, but also a gap there on the model performance side that we need to fix. And we're taking some first steps that we think to help close this gap somewhat. So that was that for the first part of the talk. I want to do the second bit, aware of time. So if it's okay, I'll just go through the second quickly and then maybe come back for questions if there are questions all the way through. So the second one is also looking at various kinds of data concerns with EHR data. This is work led by Michael Warno and Suhana Bedi. So again, lots of credit to the students that have led this work and with some amazing colleagues once again. So this is tight related to the earlier work. Again, we're looking at what happens. In this case, we're looking at supervised tasks, but still the issue is some of the biases that we found in existing data, existing models, where patients have, 10,000s of events. As already shown in a previous work, existing models don't seem to handle this all that well. Part of the issue is that as the event size starts to get longer, you need longer context in the model to handle this, at least if you're going to handle this using sort of context approaches. And existing work has not actually tested how well long context models can do in the HR setting. So if you look, we did a bit of a evaluation at the time of publication on existing literature in this work. And the vast majority were fairly short context length. The longest that we found was roughly 8,000 sort of length context, which is again much smaller than what we think is needed for handling some of the complexity, for particularly just having very long visit histories. And so some of our questions here are specifically targeting the extent to which long context might matter for EHR data. And as highlighted all the way through, thinking about EHR data properties and sort of why long context matters. So both a pure engineering long context can help, But also I want to dig a bit into the conceptual background of sort of why we think it matters in this way. So here I'll go through experiments directly. So again, looking at some of the data from the sort of STAR database over order 3.5 roughly million examples. If you're familiar with the EHR-SHOT data set, this is the same setup as that. And each patient is converted into a list of clinical events, just as before. So things like the codes, the values, all these are encoded and tokenized. And so based on this tokenization, specifically we have three kinds of tokens, things like codes, numerical, and then categorical codes. And then we're able to train a variety of different models. So here we look at four architectures. We look at a GPT architecture, so transformer style, Llama architecture, so both transformers, and then some of the sort of RNN kinds of architectures, so Hyena, Mamba, of different kinds of parameter sizes for different context length, going all the way from 512 to 16K context length. So roughly 16 models, and we train until all the models have seen about 2 billion tokens. And the models are evaluated on EHR-SHOT tests. So this is all the tests outside of the Chexpert one, which was not as relevant for this particular evaluation. And the categories that we're interested in that we think matter quite a bit are things like the repetition of n-grams, some of the irregularity between time intervals between events. I'll talk about this a bit more. And then some of the weirdness, I think, compared to natural language and token perplexity in a way that I think is very different from what you'd normally see in existing data sets. So a bit on the data, you can look up, I believe this is public now. The EHR-SHOT data set shows all the different tests and some of the existing evaluation that has been done here. And so we do some of this evaluation. Some of the things to notice, so here are some early results, some of the existing results shown in the paper. So the sort of high level, I guess banner headline is that we find the longest context model that we were able to train, which is the Mamba 16K model, seemed to perform better than many of the other models. So this hypothesis is at least partially shown correct, which is longer context leads to better models. There's a lot of weirdness with Hyena versus Mamba. So again, these are two kinds of RNN kinds of models. We don't have a good signal. This is an experimental observation of Hyena actually sort of peaking, and then this is the red curve, by the way, if you can see this on the left, peaking and then getting worse as we increase context. We're trying to explain what happened there, but it is a bit of a weird observation. The other thing you'll notice is that for the transformer models, we topped out around 4,000 or so context length. This is mostly a sort of resource challenge. So at least with academic resources, transformers scale much worse than RNN architectures with context length. Roughly rule of thumb, unless you do quite special engineering, you're looking at roughly quadratic like resource requirements as you increase context size, whereas like RNN kinds of models are close to linear with context length. And so they're sort of engineering backend trickiness that blocks how well we can handle longer context length. So the part of this is why we are limited to shorter context length. So again, the sort of high level takeaway hypotheses here. One, whether context length matters, we think there are strong signals that it does. And this is a way to sort of improve many of the language models for clinical, particularly EHR kinds of use cases. And then, again, some of the engineering gaps in trying to use transformer models, which are the dominant approach, as you might know, but have meaningful resource sort of technical difficulties if you really want to scale on the context length side. So other things to mention, some of which I think I find quite interesting and I think is worth the community thinking about more. There's some work on this. I think too little. So part of my goal, ulterior motive here, is to highlight some of these gaps that we can engage with some more. So one is this copy forwarding. So this is a standard thing in most clinical notes is that in every visit, when I get sort of the EHR for the next visit, there's a bunch of copy paste from previous visits, which is used to give billing usually context about what's happening in a current visit based on previous visits. So this is standard. This is called copy forwarding. The effect of this is that you have this sort of high repetition tokens at the beginning of every clinical note, which is like repetition from previous notes in a way that compounds in a quite, I think, different and interesting way compared to what you see in natural language. Because natural language, there's an implicit assumption that context is maintained by the language itself. And so there's no need at the beginning of every, say, sentence to repeat a bunch of previous stuff over and over and over again. In clinical notes, the standard practice is to do this repetition. Again, arguably for very reasonable human reasons, but this creates, I think, interesting data distribution dynamics that we think has a meaningful effect on the models that one is building. There's also interesting observations about irregular intervals between tokens. So, in standard language, we generally don't think of language tokens as having a lot of temporal valence. And so we think of, roughly, if I'm telling, this is not completely true. I think sometimes in storytelling, we go through time in various interesting ways. But to first order, most natural language text can be thought of as roughly temporally aligned, happening around the same time. This is very clearly, obviously not true in many EHR data sets. So you can go all the way from, tokens actually capturing something that's sort of 7 minutes time delay between when things are happening, all the way to years in between, say, copy forwarded visits signals. So, say a medication that was prescribed and then a year later a new visit. But in the token setup, these will all show up as sort of just part of a single token sequence in a clinical note because of the nature of the data. We think this quite significant irregular temporal valence actually has a meaningful effect on how well the models can capture information and sort of make good inferences and predictions based on these signals. And then finally, this observation of, in natural language generally, the observation is that text actually gets much more predictable as you go forward in time. So the way that we see this generally is we measure perplexity. As you may know, models are initially trained to be next word predictors. The more text they see, the better they are at predicting the next word as a default. And so your perplexity tends to go down with the length of text. You're much more likely to be able to predict the next word in a long sequence. Say if you've read a whole story, being able to complete the last word in an entire story tends to be easier as the length of the story gets longer. Weirdly, this is often not true in clinical EHR notes. And the reason this can be validated is that this is modeling individual disease outcomes. And often disease treatment and disease care, but also disease, the way disease exhibits for individuals often gets more complicated with time. And so you have this weird, I think, two-language behavior where actually the thing you're modeling is getting more complicated over time. And so your predictability, particularly for, say, disease outcome or disease care, can actually get worse with time or plateau in different ways, as opposed to getting simpler as you normally get in natural language. So a lot of these we show empirically, so I'll just show briefly. So for instance, for this copy forwarding, we show looking at repetition of different versions of engrams. And what you see in natural language is, again, a much, much flatter distribution than you see in EHR, where sorry, I said that the complete opposite way. So in natural language, you tend to have sort of a much less repetition. So the distribution of repetition is peaked towards 0. In EHR, you have much more spread of repetition, partially because of this copy forwarding idea. So you have many more tokens that show up sort of as a meaningful fraction of the data set because they get repeated over and over the sort of repeated clinical notes. So again, we see this as something that has a meaningful effect on how well out of the box language models work for clinical contexts. Second one is this idea of irregular token intervals. So looking at mean times between events across something like clinical notes, we again see like high irregularity and something that looks very different than what you might have imagined and arguably what the models were initially trained for say standard language models, because those were built for, again, very different setting where up to first order, event times are roughly regular, whereas event times in clinical settings, again, can have this huge distribution between them. Finally, this disease distribution and sort of complexity grown over time. So we observe this. Again, this matches some intuition where you see higher complexity as the token position increases, which is completely opposite to what you expect to see for most language, where again, you expect to see more predictability. So as you increase token position, you actually expect to see like very quick drop off in perplexity. So easier to predict future tokens from earlier tokens. Here, because again, care and disease itself gets more complicated, you have in some ways the opposite effect. So harder predictability because again, everything is getting more complicated in interesting ways. So all these we think are important properties. We think long context seems to be a way to move the needle in this direction. So make some of these issues better. We think they're meaningfully understudied. So we think of long context as sort of one way to do this. But we think, and I'd argue there's a lot more opportunity to think about other kinds of either modeling or data mechanisms to make these kinds of issues better if we're going to use these kinds of models. Or we build other kinds of models that better capture all of the properties, in this case, data and distributional properties of EHR data. And so we find, again, that models do worse when these properties are increased. Some of this is in the paper. Again, context seems to be one way to mitigate some of these issues. Okay, so to summarize, I talked through two papers, both looking at longitudinal issues with healthcare records when we try to apply language models out of the box. I talked through in instruction tuning settings, issues with temporal distribution of events, some of our work trying to build benchmarks, and also new models that better approach this. And second, I talked about other kinds of data biases that again, seem quite special to EHR data sets. And an approach, again, I think of as a first step, trying to use long context as a way to better handle this, showing some initial results where we can get better performance using longer context models. And then again, think about this as a path that we can build quite a bit towards. Okay, so to summarize, we think EHR data is meaningfully different than standard language data. Many of the issues are not well handled by current approaches. I've talked through some of what we've observed in my group and with collaborators. I think, if you're thinking about this and you find other things that we might be missing, I'd love to hear more from your observations. We've looked through a variety of longer context models as partial mitigations for these issues. Again, I think there are potential for new architectures or other ways of thinking about sort of foundational approaches that make these issues better. Lots of work to do in thinking about additional kinds of evaluation data sets. Lots of work to do to think about better improving our task design to better capture, again, what we think will be important for really getting these things to work in practice in the real world. So I'll end there. I got a few minutes for questions, but thank my collaborators and funding agencies for being able to do some of this work.
Great. Thank you. Thank you, Sanmi. For the audience, feel free to type in your question in the chat or just directly ask the speaker. So I'll start by asking one question about the second paper you're talking about, Sanmi, which is quite interesting, looking at there's this one part you mentioned, this some clinical texts are copy forward, and then there's other non-copy forward text. Do you think it's easy, or is it easy to detect all this copy forward part, or does it make sense to differentiate them in the modeling part?
This is an interesting question. We didn't try this, but I think I'll restate what you're saying as, there's a data intervention that's an alternative to modeling, right? Which is, I just filter out stuff that's repeated. As long as I do that well enough, maybe I can handle, or at least that particular issue, this sort of token repetition issue, doesn't show up in the same way. We're playing a little bit with this to see what happens. I think some of the worries here are sort of, it's tied a bit to the first paper, is we think our models still need some work to better capture sufficient context anyway. And so the copy forward, it's really built for human context. right? So it's a back-end way to get human context, at least for billing, but also sometimes for clinicians, to work a bit better. It does seem to be valuable for model context as well, to sort of have stuff closer to when modeling and decision making needs to be made. I think it's an interesting question to say, are the models good enough to actually not copy forward in this way, and so handle this by sort of just getting the longer context of the sequence of clinical events for the patients better managed? I think it's an interesting question. We haven't studied this yet, but I think it's an interesting alternative route to engage in this.
And on your first paper, the timer work, which is fascinating, and the benchmark side, you did the clinical validation. I think you mentioned like a 400 examples or so. The instruction data set, how big is that? Do we need like?
It should be. I'll double check. It's on the.
I think in your paper you mentioned like a few thousands.
Sort of. It's a high hundreds. I think it was 600 and something. So like under 1,000. Sorry, that's for eval. I should know this much more quickly. I remember it as a few hundred. Yeah, so the benchmark data set is, so roughly 400 something. Instruction, response, time evidence, triples.
No, I mean, you have this timer instruct data set. I guess that's how you used to train fine tune the model, right?
So the benchmark is smaller. The data set used for training, it's in the thousands range. I don't have it.
I think in the paper I saw some number like a 5,000 or something. And
yeah, that sounds right to me.
I wonder, with that, do you think we need more than that, or that's like sufficient to?
Yeah, no, this is a harder question of like sample, like how big a sample do we need to train these things? Instruction tuning data sets, so far, as many of you know, so the short answer is it's probably of the right order. With synthetic data, I think, the big plus is, again, the ability to scale much easier. I think the worry always is it's hard to know what you're not covering with synthetic data versus real data tends to be at least more likely that you'll catch on the edges of what you're not getting. So the short version is it's probably of the right order. And I say this mostly from rules of thumb from existing. So like even for very large foundation model companies, pre-training from the internet, order, billions, trillions of examples, instruction fine-tuning, order thousands and hundreds of thousands, sort of roughly sample size. So a few orders of magnitude smaller. And this seems to be working well as like back of the envelope recipe for most of what people have done successfully to scale up foundation models. So to the extent that the recipe is correct, I think 5,000 or a few thousand is probably the right order for instruction tuning. I'll leave open the possibility that the recipe is not correct. And so like the whole field is doing something incorrect in terms of thinking about how we scale or the relative size of instruction tuning versus the rest of the infrastructure. But to the extent that, again, the standard practice is like a good guide for what to pick, it's roughly of the same order.
Interesting. Cool. There were some questions in the chat. I guess one question about what about prompting? What can that be used to solve the copy forwarding issues with more careful prompting?
Maybe. I think of the prompting. Actually, maybe I can look at the question. I don't think I fully understand it. So it's not obvious to me how the prompting can solve the copy forward, but if someone wanted to ask, I'm happy to engage a bit more.
Just really quickly, this copy forwarding issue stayed as an issue primarily in training or during some kind of application or inference?
So it shows up. The argument I'm making is that it's a sort of training fine-tuning issue, uh, and leads to very different data distribution than you'd see in natural language. And because of this, this is a part of the sort of observation that natural language data statistics looks very different from EHR data statistics, which is a push towards thinking about other ways to handle, again, the fact that our intuition is built mostly on language, may or may not transfer well to EHR. So a good example might be, Jimeng's question about instruction tuning. The intuition there is built from what we've done for natural language. Is it the right intuition if we're going to do this for EHR kinds of settings? So it's in training, and it's again thinking through data distributional differences that likely have an impact, and again some initial work trying to use context length as a way to mitigate some of these issues. Does that answer or frame your question? So your question was about
it does. So, but and I don't want to take up too much time, so I'll just leave it with this. Is it these ICD codes or all of these like coded tokens, if you transform them into, say, some kind of natural language representation of what the code means, for example, heart failure, then is that somehow?
It doesn't fix some of the broader issues that I talked about. I think, it would still have, say, disease complexity increasing over time, copy forwarding, you'd have to fix some other way. It's an interesting point though, is part of the gap the unnaturalness of this data compared to unnatural, thought of as comparison to existing natural language data. Right. We've played a little bit with it, not that much. I think initial experimentation suggests, at least at sort of small scale, it doesn't help that much to translate, and you have issues translating back correct with it. But I want to say these are extremely preliminary, so I don't want to make any quite strong claim about whether doing translation, which is easy. Forward translation is easy, right? You can take the code and just write the description of the code. Backward translation is harder. And performance-wise, we're not seeing, at least at small scale experiments, much benefits from doing translation.
Great, thank you.
So I know we're running out of time, just very quickly, Sanmi, on the folks asking for training the long context models, those are, you're using the open source data set you mentioned, or is you have some for that?
I believe the data is now public. At the time the paper was out,
so that's this star data set, or?
Yeah, so star OMAP is not public. The things that are public, so Timer Bench is public, I should say this. So the data set there we're releasing or in process. For the second one, EHRSHOT, which is the basis of the work that we're doing, I'm reasonably certain was released pretty recently. So there should be enough signal. I guess short version is there's enough data that's public to replicate the results, if that's sort of the rough question that's being asked.
Okay, and maybe the last question there is on so here this model, the input data are all those event sequences data, right? Have you used those time series data like a vital sign or those other modality of data in this model, or not?
Yeah, so some of it shows up. So we're looking at, it depends on, I guess, are you talking about something like at a level of on an ECG time series or something like that? So at that level of resolution, no, but we have, say, chronological signals from patients over time that we're looking at. So like lab values over time, other kinds of patient timeline. So stuff at the patient timeline level, yes. Stuff at lower resolution, there might be time series within the patient, no. If that was the question, then yes, that's what we're looking at versus not looking at. That's an interesting question because again, it brings yet another level of abstraction on data resolution, temporal resolution, right? So something at the level of, say, within a single scan, you get a time series there. Interesting question. I'd imagine it makes all the issues I brought up much worse. My initial thought is that it makes some of those issues more challenging, because yet another sort of bigger difference from what you might expect in language. And so
recording stopped.
Yeah, we may need different tools for it. Okay, I think we might also have killed the hour. So Zoom, something stopped.
Yeah, the recording. I don't know what's happened there. Someone was recording on the side probably. But this is fascinating, Sammy. So are you looking at other modality of data moving forward? Like, because a lot of people are looking at imaging, time series beyond nodes and structured data, or you think this structure?
In the short term, still mostly text. There are lots of great colleagues here, Kurt, actually, folks you might know, who have done a bunch more on the imaging side. That every once in a while we chat through some of these things. So far, I've mostly done sort of text clinical note work in this direction now. I think for sure understanding better, again, I guess the premise of the whole thing is what do we think is special about health data, and what can we do to then better build tools that do better for these settings? Is there anything special? Actually, that's the even more foundational question. I think one that has shown up a ton, right? Like, can everything be off the shelf that's sort of built for general machine learning, or do we need to specialize somehow for clinical data settings of various kinds? And I think the answer is still mixed. I think even with the many years of many of us that have worked in this space, I think the data does seem meaningfully different in many settings, but I think evidence, goes back and forth. For EHRs, though, it does seem like there's some, again, meaningful gaps that either we come up with some, say, data filtering mechanism to deal with, or maybe models that are big enough can handle, which is, again, the bet in the long context. For imaging, again, I've done a bunch of work, some with you actually thinking about this. Again, I think evidence is mixed. Some properties are very nice for medical imaging. You tend to have registration, so roughly it's easier to align images across individuals than it is for natural images, where alignment may not make sense. Maybe that reduces degrees of freedom, makes it easier to predict, but then you're typically looking for sort of very precise signals as opposed to what you might be looking for in natural images. Again, there, I think evidence is mixed, where we've seen sometimes lots of benefit from very specialized model architectures and learning approaches. Sometimes, bigger, well-developed models seem to do something interesting out of the box. With a little bit of fine-tuning for imaging. So I don't know that we have a clean answer. I know your question was imaging. I've reflected this as a question more broadly about, again, sort of AI and health, and to what extent. Because to me, again, I think this is the most fascinating foundational question, is what's special, and to what extent do we need special tooling for this? And I think, for better or worse, we still have mixed evidence to answer this question.
Cool. Maybe a very short last question. I'm very curious. You co-founded this virtual AI. I saw several other well-known faculties also part of that team. Can you say a little bit more about what is virtual AI? What are you guys working on?
I'm very happy to. Always happy to shill for the company. So Virtual AI is built as a company to make it easier for enterprises broadly, is our initial main target, to deploy generative AI tools because we think about mitigating safety and security issues. So as many of you know, and tied to this presentation here, AI tools are getting a lot better, but they still have specific failure modes that lead to gaps in possible deployment. So people can't deploy because they worry about sort of safety issues, security issues, jailbreaks, PII leakage, hallucination issues, a whole bunch of these other problems. And so we've built a variety of different tools that allow for discoverability, so algorithmic red teaming approaches, and also mitigation, so guardrail approaches that close this gap and make it easier to deploy generative AI tools in particular for various kinds of real-world use cases.
do you provide mostly like an evaluation framework to validate their existing?
Yeah, so it's both
model?
evaluation and mitigation. So, and we actually think the combination matters a lot. So, evaluation, like you said, that can help you discover the properties of your models and the gaps in its behavior, and then guardrails, which are one of the ways that one can mitigate. You can also do, other kinds of tooling, but guardrails have this benefit of they can sit external to the tool, so you don't need to change your model. So they would, for instance, block behavior from either users or models that are considered inappropriate for various reasons. So jailbreak blocks, PII leakage blocks, other kinds of issues that can show up in generative AI deployments.
Cool, that's exciting. Okay.
Yeah, it's fun stuff.
That's great. Thanks, Sanmi, for spending the time with us. This is great.
Yeah, thanks for having me. Thanks for the questions as well. It's a good chat.
Thank you, everyone. Take care.
Thanks.